Okay, let's begin. So we're going to continue by going through these examples, and yeah, using some. So we already have two things here that we have to memorize for the quiz. One of these, I believe, was a quiz problem, part C. So if you tried to work through these ahead of time, that would have made things a little easier. But let's continue. So we're going to quickly knock these out. Then I actually want to talk about integration in general, and that's going to be the class. So hopefully you guys tried some of these already, so it'll go by quickly. But let's actually begin. So last time we talked about the Weierstrass substitution. What was the actual substitution? U equals tangent of x over 2, which means your x is going to be an inverse trig function, it's an inverse tangent function. If you make that substitution, what does your dx become?
2 over 1 plus 2 squared.
What would your sine of x be?
2u over 1 plus 2 squared.
What would your cosine of x be? Right. So you had those memorized, or if you don't memorize it, you could actually derive those from using the right triangle on this guy and using SOHCAHTOA and the double angle formulas. But I guess if you have those memorized, it just makes things that much more efficient. So, A. Now we're going to do this via a Weierstrass substitution, but it's starred because there's actually probably a better way to actually approach it than a Weierstrass substitution. So maybe any ideas for a different way? And then we'll actually go through the Weierstrass substitution and do it that way. A better way than Weierstrass.
Multiply by 1 minus sine x over 1 minus sine x. I think over.
What would that accomplish?
That would give you on the top 1 minus sine x, and at the bottom you would get
1 minus sine squared x
sine squared x
by difference of squares formula, that which is,
and then you can use the identity.
that's cosine squared. Then
Substitute 1 minus sine x,
no.
or I guess cosine. No.
Ideas from this point? Yeah?
You can break it apart into 1 minus cosines, 1 over minus.
1 over cosine squared, which is secant squared,
Yeah.
and then sine x over cosine x, which is cosine squared. This?
Tangent.
Tangent. How do you do with that part?
That's tangent
secant.
secant.
Huh?
That's minus tangent secant, because you can break it apart into sine over cosine and then 1 over cosine, which is tangent times secant.
Right. So this is secant squared, and this is secant times tangent. And so the integral of this,
Tangent.
and the integral of that
Secant.
is secant. So that's another way to do it. And another option here, you could have done a u equals cosine of x, or du would be minus sine of x. You can still get through that. So that was another way to do it. Had I wanted to use the Weierstrass substitution, though, what would it look like? So my integral would become
1 plus 1 plus.
and I literally substitute this expression for the sine x. So it's 2u over 1 plus u squared And for the dx, I literally substitute this expression. Of course, here at the integral of 2 over, this would be 1 plus u squared plus 2u.
Why did you multiply the 2 over 1 plus u?
Because, you're.
I just multiply it across so that I kill the compound fraction.
Oh, okay.
So I take the 1 plus u squared times the 1, I get 1 plus u squared. 1 plus u squared times this, the denominator cancels, I have that. This is actually, that's factorable. That's u plus 1 all squared. And that's actually integrable. What's that?
Negative 2 times, or negative 2 over u plus 1. Let's see.
Yeah.
And your u is
Tan of x over
tangent of x over 2 plus 1
Yeah.
plus c. And that's what it will look like by our Weierstrass substitution. So here, technically, you can do another substitution, t equals u plus 1. That just becomes 2t to the minus 2. You integrate that with the power rule. You'll get minus 1 over t. And that would be, yeah,
How can you check their equivalency?
trig identities manipulation.
Oh, it's just
So,
okay.
yeah. We're actually going to do that with part F. So, won't waste time on this one here. But yeah, just a matter of applying trig identities. As long as one is the other one plus possibly a constant, we're okay by the rules of antiderivatives. So yeah, 2 ways to approach this problem. Had I just seen this on a test or something, I probably would have done it what I did in green, but the Weierstrass substitution is another option. Now, if you look at B, suddenly the trick that we tried before doesn't seem as viable because of the 3 and the 2, the different coefficients here. It's kind of going to mess it up.
You can still use it.
So somehow this one just doesn't lend itself as easily to applying a trig identity as the last one did. Even if we try to take advantage of difference of squares, I'm going to end up with 9 minus 4 sine squared. Like, what am I going to do with that? So I probably jump straight into Weierstrass substitution. This is going to be equal to 1 over 3 minus. Now the sine of x is 2u over 1 plus u squared, so it becomes 4u over 1 plus u squared. My dx is going to be 2 over 1 plus u squared du. This is going to be 2 over 3 plus 3u squared minus 4u. So with the Weierstrass substitution, that's what our integral becomes. What now?
I mean, it's an ugly factor.
Huh?
It can be factored, it's just not very nice.
Oh, is it? What would you
It
find?
has radicals.
Yeah.
It's not a fun. It took a long time to figure out.
So you actually factored it with radicals?
It's nasty.
Yeah, let's say I don't want to do that.
Don't do that.
Yeah, let's not.
Yeah.
What's another option?
Uh,
Something doesn't factor nicely, what do we do?
Can't do so. Can you complete this way?
Complete
I
this
I
way.
guess that's the.
Complete this way.
So, I can factor out a third, that's u squared minus 4 over 3u plus 1. So completing the square for this is going to look like what? U minus 2 over 3 squared. That's going to give us, if we multiply out, that gives us 4 over 3. 4 over 9. To get at the 1, what do I do?
Plus 5.
Plus 5. Now, that in and of itself is kind of messy, but it's not as messy as things would be if I factored and used radicals here. We are going to have some radicals. What I would do in addition to this is factor out 5 over 9 from the denominator. Maybe also take out the 2. I would have 1 over. So this would be 3 over radical 5 times u minus 2/3. Why did I do that? Huh? Yeah? Because it looks like inverse tangent, right? So that might seem like something totally random, like why would he do that and make it get, why, he had like fractions here, which yeah, they're like horrible enough, but then he factored this thing out to get that ugly thing. Why? Because I have a rule in my head that says if I have 1 over some variable squared plus 1, that gives me an inverse tangent. So I want it to look like that. You can actually see this by setting t equals 3 over radical 5 u minus 2/3. Your dt is going to be pretty much 3 over radical 5 du. And so this guy would become 2/3 times 9 over 5 times radical 5 over 3 times 1 over t squared plus 1. That guy is my inverse tangent. And this can be simplified here. So kills all the 9s here. This goes into that. So this is 2 over radical 5 times the inverse tangent. So now my t is just going to be this, and at the same time my u is tangent of x over 2. So I'm going to take this, plug into here. So that's 2 over the square root of 5 times the tangent inverse of 3 over radical 5 tangent of x over 2 minus 2/3. And yeah, it's a little bit messy, but it's not as messy as
Yeah.
I would think factoring and getting the radicals would have been. So yeah, that's kind of a general principle. Of course, if you have a rational function, one of the first things you should be thinking about is trying to get a substitution to work out. If that doesn't happen and the denominator doesn't factor, so a partial fraction doesn't get to work out, completing the square is probably going to be your next best bet, especially if you have an even power in play. Yep, so that's that. Other questions on these? All right, let's see the quiz problem. Let's see what happens.
And we all know how to do it.
Now we didn't do a lot of practice on Weierstrass here, so I wanted to be as fair as possible for the quiz. Both versions actually had the same problem. The difference is I just, for one version, I switched the tangent and the sine. I wrote it as tangent x plus sine x. So won't always make them that similar, but in this case I think it was nicer to do that. Hopefully no one actually did this and were like, damn it, I know what to do with sine x plus tangent x, but I don't know what to do with tangent x plus sine. You laugh, but things like that mess students up all the time. You just write something in a slightly different way, throws them completely off.
You just don't know what to do at all.
What?
Or we just don't know how to do it at all, regardless of order.
But let's actually try to apply the Weierstrass substitution. What would that look like here? What happens to the sine x?
2u plus 2 squared.
And the tangent x?
2u over 1 plus u squared over
2u over
1 plus u
1 minus u squared, right? So how do you figure out the tangent? Is you divide the sine by the cosine, right? So the sine was 2u over 1 plus u squared. You're going to divide that by 1 minus u squared over 1 plus u squared. Keep, change, flip. The 1 plus u squares are going to cancel out, and you end up with that. where dx is going to be 2 over 1 plus u squared du. So starts out looking a little messy, but we're just going to go through here and start to clean things up a bit. Multiplying the 1 plus u squared in.
Can you factor out the 2u first? To make it easier to look at.
I could, but that's factoring out in the denominator. I'll say that. We might get to a point where I need that, but I'm actually more worried about this 1 minus u squared in the denominator here.
Times 2.
So that's going to be 2u plus 2u cubed over 1 minus u squared du. All right. What do we do with that one?
Can you sub for this?
You can write 2u in terms of 1 minus u squared on the denominator, so it would be 2u minus 2u cubed over 1 minus u squared plus 2u cubed over 1 minus u squared.
Oh, you're talking about creating a common denominator?
Yeah.
Yep, we could do that. Nicer ways to just multiply by the common denominator. Multiply and divide by 1 minus u squared. We'll accomplish the same thing in one less step. So what we have now is 2 times 1 minus u squared over, here I would have 2u minus 2u cubed plus 2u cubed. The cubes actually die. And so this just becomes 2 times 1 minus u squared over 4u. Did that for u. So this now, the 2 cancels into the 4, so this is 1/2 times the integral of 1 over u minus u. So start out a little bit ugly, but you can actually simplify it by multiplying and dividing by the LCD. And it actually works out nicely. So integral of 1 over u.
Absolute value.
ln of the absolute value of u minus
U squared.
u squared over 2. And our u is tangent x over 2. That's what the quiz answer should have looked like. Anyone get that?
I don't think so.
Don't worry, there's always next week. There's always test 1. And after test 1, there's always the final. But then that's it. Like, we don't have to get our shit together by then.
All hope are encouraged in the test. The hopes in the future.
D. So that green asterisk means there was another way to do this problem. Let's do it that way first. Perhaps a better way? Ideas?
Double angle form.
What would the double angle formula tell us?
The cosine 2x turns into cosine squared x minus sine squared x.
Okay, and? That's actually true, but there's a nicer one of those identities.
Is it the 2 cosine squared x minus 1?
You can replace cosine 2x with 2 cosine squared x minus 1.
Yeah.
That will kill the plus 1. And that's actually just 2 cosine squared x. So this is just 1/2 times integral of secant squared x. So that's 1/2 tangent x. So that was actually not bad, but for the sake of practice, let's actually try doing this with Weierstrass-esque substitution. The idea here being, because my angle is a double angle, I also double up on the angle in the Weierstrass substitution, so instead of x over 2, I just use x. And the point of asking you to do this is just to kind of force you to go through the steps and derive what the substitutions would actually look like, so that you would remember. If you don't have the formulas memorized for the quiz, this would have given you the practice needed to derive the formulas on the spot. So let's actually do that. We're going to rederive the Weierstrass substitution formulas with a double angle instead of the half angle. So for u is equal to tangent x, this means I think of this as u over 1, which means I can draw a triangle where x is the angle, tangent is opposite over adjacent, so this is going to be 1 plus u squared rooted. So from that, I can get that the sine of x is going to be equal to opposite over hypotenuse, and the cosine of x is going to be equal to adjacent over hypotenuse. I can also, from this, figure out that if my x is tangent inverse of u, then my dx is just going to be 1 over 1 plus u squared du. And yeah, I can go, these two together would of course imply that the cosine of 2x is going to be equal to, say, cosine squared x minus sine squared x. And so I'm going to take this squared minus that squared. I'll actually look at 1 minus u squared over 1 plus u squared. So doing this version of the Weierstrass substitution, the only thing that really changes is actually the 2 here is no longer a 2. That being said, applying that to this integral, cosine 2x I'm going to replace with this, so it's 1 plus 1 minus u squared over 1 plus u squared times 1 over 1 plus u squared. This is going to be 1 plus u squared plus 1 minus u squared du. Those guys are guys, so it's just an integral of half du. So this is just u over 2 plus c. And so our u, the substitution was tangent x. So this is tangent x over 2 plus c, which actually directly coincides with that answer. So a little bit of work here, but there was a much nicer way to actually do this particular problem. So this one, again, doesn't really lend itself to a nice trig identity. So I'll just jump into Weierstrass. This guy is going to look like 1 over the sine of x is 2u over 1 plus u squared. Cosine of x is 1 minus u squared over 1 plus u squared. 1 is just 1. This is 2 over 1 plus u squared u. squares die. That's our guy. So that's just so you do that. Oh, it's not so bad. Now for the moment we've all been waiting for. I'm so sorry. We're going to find another way to integrate the secant x function. Not that we don't know how to do it already, but the way we did it was kind of mysterious. You multiplied and divide by this weird thing, like who would have thought of that? It turns out it was a stroke of genius, but it happened in hindsight. Most people probably wouldn't see that, the typical Calc 2 student. So let's kind of do a more direct plan of attack here, and we can now do that with the Weierstrass substitution. So now you've noticed that that is just a rational trig function. So we know that this is going to be 1 over cosine of x, and we know how to represent the cosine of x with the Weierstrass. So by Weierstrass, this guy is going to become, well, cosine of x is 1 minus u squared over 1 plus u squared, so that just becomes 1 plus u squared, or 1 minus u squared, times so we have that. This cancels out. Okay, how do we deal with that then? Partial fractions. So, going to think of this as 1 minus u squared times 1 plus u, 1 minus u times 1 plus u. And how do we find the partials here?
Plug in one.
Right, we can do the cover-up method because we have non-repeating linear factors. So, u equals 1 makes that 0. We're going to cover that up, plug in u equals 1, and we get a half. U equals minus 1 makes this 0. Cover that up, plug in minus 1, I get minus a half. So this is just the integral of 1 over 1 minus u minus 1 over 1 plus. Integral of this guy?
ln of 1, or ln of absolute value of 1 minus u. Negative, sorry.
Negative.
Negative ln of absolute value.
Right, because you'd have to do another substitution,
Yeah.
technically speaking. T equals 1 minus u, your dt is going to be minus du. So that actually gives us the answer, minus ln of 1 minus tangent of x over 2.
No, but we shouldn't do this.
Minus ln.
But it won't, it
there-
won't make it equal to like the formula. I mean, it could, but like, it doesn't need-
Coming in?
couldn't you just combine the report, the stuff before? Could you just combine it and then multiply by one plus, yeah, 1 plus u over 1 plus u.
At what point are you talking about?
The one before, you did. So ln 1 minus u, you combine them, and then multiply by the denominator and the numerator.
Where? Here?
No, that.
Down row.
Yeah, the last one.
Here. What happened?
You can combine them by making it 1 minus u over 1 plus u, and then multiply by 1 plus u.
Using logarithmic rules.
Yeah.
Oh, so you want to, yeah, but whatever we can do here, we can do over there as well, right?
Okay.
Yeah.
Second divide.
But is this right so far?
I
I think so.
I feel like
Why is there two
negative
negatives?
function.
Why is there negatives?
Well, it should.
Because I remember there not
No,
being
no.
two different signs here.
The second.
There shouldn't be
should
two negatives.
Well, you use positive there, it should be,
One plus u should be.
it's just one. So it's stays positive.
Yeah, one is.
That's fine.
Wait.
And this-
Because we had this, and I'm pretty sure we're okay up to here,
No, ln plus
right?
1 plus u.
But that second term I think should be
The second one
positive.
should be positive.
This is going to be 1 minus c times 1
It should
plus
be
c.
negative ln
We break it up.
plus ln. Yeah, how did you
Yeah,
get
plus-
negative
Second-
half
second
in
The
the
second
second
one
part?
should be positive.
No.
We
No.
covered this up and,
No.
oh, because
And
there's
that's
a
two
negative
double
here,
positives,
so,
double
yeah.
back.
Yeah.
Yeah, so that's a Yeah. plus.
Yeah.
Yeah. That makes a lot more sense.
Okay, now what? So that's the answer according to Weierstrass.
But then we have to turn it into the point.
Is that actually the answer? Did anyone actually figure it out? How can you make that equivalent to what we know the answer to be? Ideas?
How do we make it, well, and this is.
Come here. I think we're doing okay. Ideas?
I
Yeah.
use double.
I'm sure that's what we have to do, we have to use the double angle formula for tangent.
You mean a half angle formula?
Yeah, the half angle, sorry.
I don't even remember what that is. Do you remember what that is?
No.
You don't use that often enough to remember.
Could you combine them?
I mean, we could derive it, but is it worth it? I don't know.
Is it?
Could you
is it
combine?
Probably instead of using the tangents, I would change the sines and cosines.
Maybe then you would use a half angle one?
Can we combine it? Yeah.
I can write it as that. And probably switch the sines and cosines. So this is sine of x over 2 over cosine of x over 2 over 1 minus sine of x over 2 over cosine of x over 2.
And you multiply by,
What's an acceptable Pearson
Huh?
answer?
and then you multiply,
Multiply by cosines over 2 over cosines over 2.
no, 1 plus cosine of x over cosine x from both.
And I'd probably want to get rid of the compound fractions first. If I multiply by cosine x over 2 over itself, now do you guys see what to do? I think there's hope here.
Could we multiply?
There is or isn't?
X over 2 plus sine of x over 2 over cosine of x over 2 minus sine of x over 2.
Multiply by cosine.
Yeah, multiply by cosine x over 2 plus sine x over 2. Now, what that's going to do in the denominator is I'm going to get a cosine squared x over 2 minus a sine squared x over 2, which is cosine x, right, by the doubling form. And in the top, I'm going to get cosine squared plus sine squared, which is 1, plus 2 sine x over 2 cosine x over 2.
Wait. Is the 1 over 2 then? Oh no. The angle doesn't matter in the identity, right? Okay, never mind.
So it should be ln.
And this is,
That's sine of x.
that's actually sine of x.
Cool.
So I end up with 1 over cosine plus sine over cosine. What's that? That's
That's secant
plus tangent. So these are exactly the same thing. So that's the form that we had memorized.
See what memorization is?
So you could have, you know, if you had to figure this out, you could have done a Weierstrass, and then to clean it up, if you don't like half-angle formulas, you could eventually get to this point here.
Yeah.
I just think it's a nice application of Weierstrass here. Something that's not totally out of the blue.
Yeah, it's
Now,
not.
of course, you have to do a little more work to get it to get back to a form that you're familiar with. But I mean,
It's not purely out of imagination, so.
it's not like, how did you see it? It's not like out of thin air. It's something that's more direct. You have an actual strategy here, which is what I want to talk about now. Strategy. So, as you've probably garnered from the quizzes, the last few quizzes we've had, knowing about integration strategy is going to be important in this class. You know, you need to know how to actually look at an integral and know what to do. What's your plan of attack? How to figure these guys out, because you are going to have to be able to do integrals relatively quickly. So, ultimately, there is a standard that I have to prepare you guys for, and pretty much it's going to be, you need to do like 4 or 5 random integrals in about 15 minutes. So I'll tend to time my quizzes to kind of match that, so you're matching the level at which you're going to have to perform by the end of the semester. Now, that being said, how do we actually go about doing this without like
Messing up.
like randomly going down the wrong path or being like a chicken with our heads cut off? How do we actually do this thing right? And so that's what we're going to do now. We're going to continue the art of integration. We're going to finish that, we're going to finish the book. So I probably don't want us to call it a strategy or the steps to do an integration problem, because it does have its nuances, right? It's not called one anymore. So let's finish this strategies. Faced with a random integral, okay? So a random integral show up on your quiz, on your test, or whatever, right? So it's some random f of x dx. How do we compute it?
Cannot.
What goes through your mind? What do you try first? What do you try second? What do you try third? What do you try fourth? What are the ways that you can actually come up with a plan of attack for some random integral? So it turns out that I mentioned these to you before, but the first 3 steps are pretty much set in stone. We always do the first 3 things in order. Step 1. What was step 1?
Basic rules.
Try to apply a basic rule. Now, what are the basic rules? These are the guys that I asked you to memorize and regurgitate on problem 1 of all the quizzes that we've had. Just kind of the elementary ideas that we have. So things like, okay, the integral of that is this. Or the integral of, say, 1 over x is ln of absolute I of x. Or the integral of e to the x is e to the x plus c, etc. Right? Guys like that, right? So there are these basic formulas and templates and rules that you know that you always try to apply first. Now, to be fair, for a class like this, I'm never going to ask you a problem where this is all you're going to need. But, we asked you problems where this is all you needed in Calc 1. We're past that now. But it is still an important step to know about, to consider, because even though you might not have a problem where this is the only thing that you're going to need, it does provide you with a lot of useful tools and insights, because what you want to think of these guys and your basic rules are, they are your templates. They are kind of, if you have something that looks more complicated like these guys, chances are you're going to want to do something to make it look like one of these guys. So you need to know what these guys are. So like earlier when I was doing one of the problems, I was factoring out this random things while completing the square because I had a rule in my head that I wanted it to look like. The 1 plus 1 over x squared gives me the arctangent, right? So instead of sitting there, well, I'm confused, I don't know what to do. Like, I know what to do. I need to aim for one of these guys. These guys are like your targets, your lighthouses. You know, so when you're out there on the ocean, just like drifting, like, no, there's a lighthouse. These are the guys. You go like, yes, e to the x. Can I make this look like e to the x? Can I make it look like 1 over 1 plus x squared? So knowing step 1, knowing the basic rules, very important, because a lot of times they're kind of who you're aiming for. And you can think of all the strategies that I tell you. Kind of the point to all of it is to bring you back to a situation where you can actually apply these rules. Whether I'm doing a substitution or a trig substitution or integration by parts, ultimately the idea is break the integral down into more manageable chunks that looks like these guys. So you need to know what these guys look like in order to even use that information. So still a very important thing, and yeah, you need to know them. Step 2. So if it doesn't look like a basic rule, what do you try?
Simplify.
Try to simplify. So try to use basic algebra to get you back to this situation is going to be the first. Try to simplify to make it a basic rule. Right, so you have something like, you know, the integral of 2x cubed plus 3x plus 1 over x cubed dx, right? Well, basically the idea is you can just divide everyone by x cubed. Now, you have something that's slightly complicated, but you can actually use the power rule for all of these terms here. So you might have something that's a little bit removed from these guys that just some simple algebra can get you back to them. So, I mean, these guys aren't unheard of. Like, I could ask you a problem where it's just that. Just a matter of applying some algebraic simplification, just like that 1 over 1 plus the cosine of 2x was kind of a guy like that. Didn't look like a basic rule, but by applying a trig identity, I got it to look like one of the basic rules. So that's all. The second thing you try. What's the third thing to try? Substitution. Substitution. Always try a substitution. Always consider, can a substitution work? Try a substitution. Right? Always going to be your third thing. The third thing that crosses your mind. Can I do a substitution here to make it look like another basic rule? So your substitution should make the integrand simpler. Now, What do you mean make it simpler? Simpler in the integration sphere means one very specific thing. Look like something in step 1. Can you do a substitution to get what you're looking at to look like one of those guys? That is simpler. These guys are the simplest things there are in the integration world. You try to get a substitution to get back to that. Now, back in Calc 1, you were told that, okay, whatever you substitute, you have to be able to see the derivative somewhere else in the function. That's no longer true, unfortunately. You might not see the derivative of your substitution. In the integrand, right? So, again, you're always going to try this third, even though at first glance it might not appear that a substitution is going to work out. Try to force it to work out, because sometimes it might not look that way at first, but it is that way. One example that we did was e to the radical of x, right? See something like that? What do? It's not obvious that a substitution would probably be the way to start this out, because, right, what would you substitute? The power makes sense. Why would I think of substituting the power? Well, it makes it look closer to this, right? I don't know how to deal with e to the radical of something, I just know how to deal with e to something, right? So your first thing would be, how do I make this look like one of those? Substituting the power is going to make sense. Now you get work, but I don't see the derivative anywhere, right? You can always kind of maneuver it in there. So you say something like t equals the square root of x. A couple ways you can do this. You can do t squared equals x. And so 2t dt equals your dx. And suddenly, the answer appears, right? So this is now 2 times t e to the t. And it's now clear that you need integration by parts to finish that out. Another one that we've seen, say like an x cubed over the square root of 1 plus x squared. Or 1 plus x squared over x. Now, probably the easiest way to attack these integrals is with a substitution. U squared equals 1 plus x squared. But it's not at all obvious that the derivative of those guys are there, right? So the derivative of this is going to give you a 2x. You don't really have a 2x, but you know you can actually break off its x squared and an x here. For this one, you multiply and divide by an x to get the x there. So you have maneuvers that you can do to get a substitution to work out, even when it's not obvious. So you always try this third. It's not always going to be painfully obvious that it is what's going to help, but it will often help. Whenever a substitution can get you to look like anything simpler, it's in general going to be easier than any of the other techniques we know about. It is always therefore step 3. You always try to substitute. Whatever you have, it kind of looks ugly or messy. You want it to look like something that you have in step 1. So that's your first consideration. Then you try to deal with the minutiae. How do I get the dx? And sometimes you can multiply and divide by something. Sometimes you just solve for the x and then just directly derive that and get the dx. There are multiple options. But you always want to try this third. So, and that's kind of where the cookie cutter advice ends. Everything else now is sort of a nuance, and while I'm going to label things step 4, step 5, they're not really step 4, step 5. So, the following are in no particular order. The first 3, you always do it in that order. Is it a basic rule? Can I simplify it to look like a basic rule? Will a substitution work? Always think those 3 things in that order every single time. However, the following are not in order. And to apply, we're assuming the first 3 steps don't work. Right? So everything I say here, this is under the assumption that steps 1 through 3 did not work, which is why we're here. order in which I presented the different techniques, but again, no particular order here. Step 4. Int by parts. Right? So you're looking at a random integral, it's not a basic rule, can't simplify it, substitution is not going to work out. Why would I think integration by parts? Why would this make sense to be, okay, maybe this technique is going to work out in my favor? It's particularly useful in 2 situations. 1, you have 2 different types of functions present. Okay, so you see something like an exponential times a trig function, or you see something like a polynomial times an exponential. Right? So, like that. Or something like that, right? You have 2 different kinds of functions being multiplied by each other. So, this is guy's an E, that guy's a T, this guy is an A, that guy is an E, right? You have 2 different classes of functions being multiplied. It's not going to 100% of the time works out, but if you see this, integration by parts might be something you would think about. So, of course, you're going to have in your mind Liate, and you're going to try to see, okay, if I make that the U and that the dV, this is what I'm going to get. Is that easier? And hopefully you get an easier integral. Sometimes you don't. So that's when integration by parts is useful. There's a second situation that's very common that you'll encounter where integration by parts would be useful. And this is, you have a function whose derivative is easy to compute. Of course, easy relative to its integral. And it would be convenient. So, a classic example here would be something like the integral of the tangent inverse function. I don't have 2 functions multiplying each other that are different types, but you know what? The derivative of tangent inverse is going to be a lot more easier to deal with than tangent inverse itself, right? The derivative of that is 1 over 1 plus x squared. So I know that if I make that the u and then dx to dv, I'm going to get an x times the 1 plus 1 over x squared. Hey, that's something that a substitution could work on, right? So its derivative is easy. I know what it is. I know how to compute it. And it's just going to be a lot more convenient. So these are the 2 main situations in which an integration by parts might be something you want to think about, right? So if you notice that, that would be probably something you want to try. Of course, there are things can be more nuanced here. Like I said, we're not in Calc 1 anymore. So, an example like secant cubed was a guy where doesn't quite fit in either one of those 2 boxes, but integration by parts is the standard way to attack that. Of course, now you could actually use a Weierstrass to attack it, but integration by parts is more traditional. And the trick here was to first break it up like that, and then notice that something like a step 2-esque should be able to work. The integral of this is going to be more convenient because then it gets me a tangent in there where I kind of know how to apply rules with tangents and secants. So that's when you might think an integration by parts. And again, it's assuming the substitution didn't work out. These are some things that you might notice. You find yourself in these situations. Hey, I have 2 different kinds of functions multiplying each other. Maybe an int by parts will work. Or, you know what, I'd rather the derivative of this guy I'm looking at than the integral of the guy I'm looking at. Maybe an integration by parts is going to work. Otherwise, it takes a little bit of ingenuity, and so that's where an int by parts could be the way to go. Step 5. These were with trig integrals. So probably the first thing you want to do is take advantage of trig identities. And when you see forms like we mentioned, like a sine to the m, cosine to the n, or you see something like a secant to the m, tangent to the n. We went through those cases, you know how to deal with them, and we also know how to deal with similar cases which involve trig identities like a sine x over a square root of 1 minus cosine x or something like that. Those guys would be, you just use trig identities, or one of the strategies that I mentioned with trig integrals. So if you see trig, you might try that. Step 5b, I guess, trig substitution. Now, trig substitution is when you don't have trig, but you introduce trigonometry into the situation to hopefully make things a little bit easier. When is that a good idea? When would you what would make you think a trig substitution might be a good idea? Yeah.
Can you see one of the forms in the denominator?
Right. Well, not necessarily the denominator, but just seeing one of these forms somewhere. What were they?
A plus x squared.
A squared plus x squared, or let's see, x squared minus a squared, or let's see, a squared minus x squared. You see one of these forms, that reminds you of a tangent, that reminds you of a secant, that reminds you of a sine function. And so you see one of these guys somewhere. More convenient, so if you see these guys, and again, we know that substitution is not going to work out. So if I had this guy, x squared over the square root of 1 minus x squared, then yeah, that's a trig sub problem. If I saw x cubed over the radical of 1 minus x squared, that is not a trig sub problem. That is a regular substitution problem. You would not use this here, right? So we're assuming step 3 didn't work out for us. But if you see any one of these scenarios, it's especially useful if they're trapped inside of radicals, but they might not be. But if you see them, you can try a trig substitution. It might work out for them. But just be aware that there are times when a regular substitution would work. For example, if there's an odd factor of x elsewhere in the function, you can probably get a regular substitution to work out. So you wouldn't actually do that. Also be aware, so maybe I'll just actually specifically mention that. Ensure a regular substitution does not work before actually trying this. Because you can actually waste a lot of time going through a trig substitution if a regular substitution would work. Also, another thing I would mention with trig substitution is to always change the limits if you have a definite integral. So you save time on the back substitution phase, which can be quite annoying. But that's a fifth thing that you can think about. Not necessarily specifically fifth in order, but if you see trig functions, can I apply some trig identity to make it look nicer? Or some strategy that goes along with certain trig forms that I know? Or there might be a case where you don't see a trig function in the beginning, but you see one of these 3 expressions. Or a similar expression. So you notice that if you had something like a 4 minus a 2x plus 1 all squared, that kind of expression does fall into this category. Right? So that's another thing that we would try. What's the other guy we looked at? Partial fractions. Saw that last time. When would a partial fractions be useful?
Polynomial over polynomial.
Right, which is called a rational function. What kind of rational functions?
A proper one.
So this is f of x is a rational function. What is the main thing that we need from our rational function?
Proper.
It's not the main thing.
Factorable.
Huh?
Factorable.
What's factorable?
Denominator.
The denominator has to be factorable. Factorable over the rational numbers. So you don't want to try a factorization with radicals and stuff like that, because you're going to have a hard time if you can even get it to work out at all. So the denominator has to be able to factor. If the denominator doesn't factor, then maybe it's a substitution problem. Maybe you try to complete the square or try something else. But partial fractions, useful when the denominator is factorable. And it's more of a side note, I would say, that make it proper if not proper. Make it proper before proceeding. So the first thing you want to check is that your denominator is factorable. Because if it's not, then you don't care that it's proper or not in any way. Right? So, and we saw ways to do this. There's algebraic manipulation. You can add and subtract something convenient, multiply and divide by something convenient, or just do a long division. But you see a rational function, the denominator factors, you might think partial fractions right away. However, you need to make sure that before going through the steps of partial fractions, you have a proper rational function. The highest part on the top must be strictly smaller than the highest part on the bottom. What else? And then we have the last guy we looked at, the Weierstrass substitution. So, when does the Weierstrass substitution work? f of x is a what? It's a rational trig function. And again, assuming some nice substitute, some nice trig identity doesn't actually help you, so like the 1 over sine x plus cosine x plus 1 dx. There are a few cases where it will work out even if it's not strictly speaking a rational trig function, but that's, I wouldn't ask you a problem with that. So it's a rational trig function, right? So it looks like a rational function, but instead of x's, you have sines of x's or cosines of x's, or you have trig functions instead of just x's. So that's where a Weierstrass substitution would be useful. If you have a rational trig function. And so, yeah, that's kind of how you would go about this whole integration game. There are certain things that you look for first, second, and third. Other than that, it depends on the situation you're in. So, fourth, integration by parts, particularly useful if you have parts that are different from one another, different classes of functions. Or you have a function where its derivative is going to be easier to do with under an integral sign than it itself. You think integration by parts. If you want to do, like, if you see trigonometry, try to apply trig identities, try to get it simpler than that. If you see those three expressions, x squared minus a squared, or a squared minus x squared, or x squared plus a squared, try a trig substitution, assuming a regular substitution is going to work out. Yeah, partial fractions, when we can factor the denominator, and just make sure it's proper afterwards. Weierstrass substitution, you have a rational trig function. And by applying a Weierstrass substitution, it will turn this into a rational function, which chances are you need partial fractions, or maybe some other technique afterwards. But that is basically the idea. That's overall the game that we're playing. There are 7 things that should be rolling around your head at the moment you see an integral. And the first 3, always those first 3, every single time in that order. Different situations will call for different things, but these are the fundamental integration techniques. So as long as you're integrating, these guys will be important. And you will go into future classes where you'll find a lot of nice theorems that makes a lot of integrals easier, and you'll see these cool techniques and stuff like that, especially in like complex analysis. But at the end of the day, knowing these things are going to be important, and you're going to a lot of times reduce other situations to guys like these using some fancy theorem, but you need to know these. These are, as long as you're integrating, these 7 things are indispensable. You must know them in order to be able to integrate properly. Okay, yeah, so that's it. That's how we integrate. And in this class, as I mentioned, you are going to be put in situations where I'm going to give you a random bunch of integrals, and you're going to need to know how to integrate them fairly quickly. So you need to be able to run through these notions in your head in fairly quick order to actually get out of it. And it's a very common thing for students to take a long time to figure out, what do I actually need to do here? What is the strat like? To get stumped. But it helps to have like a set of strategies in your mind, I think, as for what to do. And so in the last few minutes of class, I'm going to do an activity where we're going to practice all this stuff. It's not going to take very long. In fact, the whole point is to actually do it very quickly. So let's actually do that. So here are some handouts. I don't have enough for everybody because it's a lot of pages and I didn't. So the point is pass it around, but you'll have to like double up, I think, to share. And I'll post an electronic version of this so that whoever doesn't have a copy actually.
Is this one typo? That textbook is in a binder.
Maybe YouTube share, and then YouTube share, and then only one between the two. Is anyone not in a pair of people who has a group?
These are not definitions.
So everyone has access, they can see one of the papers, right? Okay, cool. So I guess we have some extras. You can take that back. Okay, all right, let's do it. So I went through a bunch of calculus textbooks, including yours, which I think is what page 1 and page 2 is, and I pretty much went to the review section for the integration. So all the integrals here, they're just a random mix of integrals. So it's not like one technique that you always need to know. It's a mixture of techniques. And I got this from several different calculus textbooks, right, from the review sections. So you have random integrals. It will tend to be different things needed for integrals in the same group of problems. So what we're going to do is, I'm going to call out some integrals. You guys are going to tell me how to do them.
Okay.
So that's the game. Here's the catch. Maximum of 5 seconds to do this. Right? The goal is to eventually be able to do this in 3 seconds. But it's your first time playing the game, so it will be nice. 5 seconds. You guys have a 5-second time limit to get the approach to the integral that I'm going to mention. Okay? Is everybody ready?
No.
Okay, all right. Okay, problem 1, page 1. Start. No, wrong. Well, step 2, guys. That's step 2. Expand and divide into each. That's going to give you the integral. Okay, problem 17. Same page. No, wrong. Partial fractions. Okay, page 2.
You gotta explain the reasoning. Explain the reason why.
No, you have to explain the reason. Okay, problem 105. No.
Partial fraction.
Page 3.
Wait, what was the answer?
Problem 1.
What was the answer for that?
We're going. Go. Page 3, problem 1.
Oh, that's Weierstrass.
Weierstrass could work. There's a nicer way.
Substitution.
Yeah, can't you just use
Regular substitution would work.
Yeah.
Like Weierstrass is like step 7, right? But step 3 can work. Problem 18, page 3.
Oh, that's
Regular substitution. Good. Problem 10, page 3.
Oh, going back. That's partial fraction? No, never mind.
It can be a partial fraction, it's not rational. Okay, you guys are dead. Moving on. Problem 47, page 4.
No, part.
No, you guys are dead. That's a substitution. Problem on the same page 4, problem 56.
That is a reason it's not partial.
No, okay, we're done.
We're not that right.
What was that?
Okay, problem page 6, problem 9.
Oh, that's you said.
What would you substitute?
LMC.
Okay, problem 10, same page.
That is that is trick substitution. That is
No, it can't be a trick sum if there's already a trick.
Also in
Okay, problem 35.
Yeah, we did this one.
Okay, you guys are dead. Problem 41, same page.
partial.
No, you could. It's not the most efficient way to do it. Substitution, what would you substitute? Right, 2x plus 1. U equals 2x plus 1. Page 7, problem 3.
Oh, that's trick substitution.
Drink sub. Problem 6.
Part. You sub then part.
U sub first, then parts. Problem 8.
You sub.
Regular substitution. Problem 8, page 8. Problem 29.
Oh, simplify.
Simplify.
Simplify to what?
Like simplify the denominators and like just step 2.
No. Alright, you guys are dead. Alright, so.
What would that do?
What was the point?
Huh?
Oh, no, you can.
Which one? The one I just said?
Yeah, the last one.
You can factor that out.
Can you factor that? X squared plus 4x plus 8?
You can pull out a 4 from the 8, make it into, you can factor that result, and then you can make it, I think, tangent, or inverse tangent would be in.
Right, there's a nicer way to say that though, right? Complete the square. And then it's going to be an inverse tangent substitution. Okay, so basically now this is the kind of thing you're going to do. And I literally mean you should be able to do this in 5 seconds, right? So you want to be able to, I give you a bunch of random integrals, right? Give you 4 problems, 15 minutes to do them. Within the first 5 seconds of looking at a problem, you should know what it is you need to get done. The other 3 minutes, 4 minutes that you need is to just write it out as a formality. Let me give Jhevon something to create. You know, it's going to be bored with this weekend. Let me just do something. But you need to know within a few seconds of looking at something how you'd actually approach the integral. And goal is going to be to get this down to 3 seconds. It is doable. It is doable to be able to look at something and in 3 seconds know that's what I need to do. Eventually, you'll be able to look at something and you'll be able to say a couple steps deep. You'll be like, oh, I'm going to do a substitution, it's going to turn to a part of fractions, and then I'm going to break off piece, and that's going to be an arcane. You'll be able to see that with practice. So you're going to practice with this. What you're going to do, make it fun. You know, you have a friend in the class, just be like, all right, let's play this game together. If you get more wrong, you buy lunch for the week, right? So I'm going to pick 10 random integrals, and I'm going to give you 30 seconds to figure them all out. You give me 10 random ones. Whoever wins, you know,
Yeah,
the other person. Like, make it fun, make it interesting, get really fast on recognizing what you have to do. So go over this and try that. I will see you guys on Wednesday.